namely that the angle product of 1, 2 times the bracket product of 1, 2 has to vanish. But all that says is that 1, 2, the angle product or the bracket product has to vanish. We don't have that both of them vanish. And if we take the momentum complex, then we can have one of them vanishing without the other vanishing. And remember, just a few minutes ago, I asked you to store in your mind the fact that epsilon plus in the standard velocity representation squared is equal to 0. It's most certainly a complex object, because it's the outer product of two complex vectors that are unrelated, two complex spinors that are unrelated, Q and K. And so it's exactly an example of the kind of thing that we're looking for. We're looking for an on-shell vector that's complex. And basically, everything that we're going to do from now on, we want in general to take this vector to be complex. And if you think about it, then you can see that if you share a reference momentum, if you have a different momentum, for example, then this statement is still true. And it's still true because we're going to get, after doing the Fierce transformation, we're going to get an angle product of Q's, and that vanishes even if the bracket product of the K's does not. So now when we do that, and we go back, then if we've chosen, for example, the bracket product to vanish, then this is perfectly well defined. It's just some complex number. This equation is a specific 3-point form of a general equation you've already seen. And these are the so-called Park-Taylor equations, which in their form, and we know today were not actually written down by Park-Taylor. So it's another example of Arnold's theorem in action. And we have 3 of those, basically telling us that if all the velocities are identical, we get 0. Or if there's one opposite velocidity, then we again get 0. And if there's 2 negative velocities, then we have that quartic form. Where the characteristic cyclic denominator. This form, again, does hold even for n equals 3. We saw that a little bit earlier. This form is actually violated for n equals 3. So this is only true for n greater than or equals 4. And that violation has to do precisely with the ability to evade the constraint of vanishing invariance by making only one or other of the flavors of spinor products to vanish. So the next thing I want to do is to start on the first of our on-shell methods. And we've already introduced complex momenta that will be important to the on-shell method. And the claim indeed is that with this 3-point amplitude, which we now have a non-vanishing form for using complex momenta, we can in fact reconstruct all 3-level amplitudes. So again, here I've shown you the gluon one, and so you can reconstruct all 3-level gluon amplitudes. If you added in the fermion and scalar ones with the general n equals 4 form, you could do all of those amplitudes. So the basic idea in these on-shell methods is that we start with the basic ingredient is this 3-point amplitude. We use only information from on-shell physical states. The way I've derived the 3-point amplitude for you, we do actually make use of a Lagrangian. There's a Lagrangian from which we got the 3-point Feynman vertex, but as I mentioned, one can actually get around that and simply derive it on general considerations of Poincare invariance. It's really the only kind of object with the right symmetries, and using then sort of a simple-minded factorization properties of the 4-point amplitudes, you can even show that the Yang-Mills interaction is the only possible one for spin 1. So you don't actually need the Lagrangian. But here we did make use of it. And the other key idea is to take general properties into calculational tools. And the first such property that we're going to talk about very briefly today, and probably come back and study a little bit more tomorrow, is factorization. And what we're going to use it for is to derive the so-called BCSW, Brito-Casazzo-Fang-Witten on-shell recursion relations. And it probably doesn't surprise anyone to know that the Casazzo here is the same Casazzo we'll be lecturing later in the week. So it's the general result in quantum field theory that when you have, for example, if you're looking at some amplitude, and so let's say some 1 plus 2 gluons go into some number of some final state, that if we have some intermediate pole as the sum of momenta of the initial state approaches that intermediate pole, then the amplitude will factorize, and we'll get the intermediate state. The intermediate state will propagate for some amount of time, and then ultimately the intermediate state will decay into whatever it was supposed to. Of course, I'm thinking about this in a crossing invariant language, so really if I have 2, or for that matter, if I have more particles whose mass approaches some intermediate state, we're going to get a factorization into 2 amplitudes along with the propagation of that intermediate state for a long amount of time. In fact, as you get close to the pole for an arbitrarily long amount of time, assuming that the state is itself doesn't have a width. And of course, this mass could be 0, so we could be thinking about factorization on fermions or on gluons. In fact, so that's what we want to do. So at tree level, in fact, in gauge theory, this is really the way it works. At loop level, things are a little bit more subtle, and we can draw a diagrammatic picture. So let's think about what happens, for example, when we have some amplitude with 3 color adjacent legs, and there's some other number of things. So as we approach a configuration where the sum of these 3 momenta becomes null, but we have each of the 2-particle invariants not being null, and I'll leave you a minute to think about how that might be possible, then we get a factorization into a 4-point amplitude times the pole times an amplitude that has 2 fewer external legs, and whose momentum is given by the sum of momentum here. So the sum of Ka, Kb, and Kc. Again, these are understood to be the sum of all tree diagrams, so this is a complete tree amplitude. We'll come back next time and look at a specific example of how this works, but I want to at least get started on the BCSW relations today. Now, the reason I started with 3-particle factorization rather than 2-particle factorization is that, again, 2-particle factorization is a little bit more subtle. So we're working with real momenta. This would now be a 3-point amplitude. It would vanish. I would now have a 0 over an infinity. And that's an object which you can actually resolve into a meaningful object, but you have to work a little bit harder at it. Fortunately, if we're working at complex momenta, then everything works the same way. And if we had 2 rather than 3 here, we simply factor into a 3-particle amplitude, a pole, and amplitude in this case with 1 fewer external legs. So again, we should be thinking entirely in terms of complex momenta. So if you haven't already realized, then that means, of course, that one of the signs of the energy has to be opposite to the signs of, let's say, the sign of the energy of A has to be opposite to that of B and C. Clearly, if they all have the same sign of energy, then these 2 statements cannot hold together. But that's, of course, possible if you have, let's say, one of the particles in the initial state and the others are in the final state. So let's skip a little bit of the discussion of some of the details of factorization, which we'll come back to, and at least get started on BCSW. I know I'm running over, and I try not to run over too much, but we will probably be here for about another, I think, 20 minutes or so. So if you have an urgent reason for needing to leave, someone can hold you back. So what we want to do is introduce a complex parameter Z. And we're going to do it as follows. We're going to do a shift of the spinners. So we have spinners that are associated with each of the external momenta, and I'm going to shift them as follows. I'm going to replace J minus Z times the other spinner, and I'm going to replace L plus by L plus Z times the first spinner. What does that do to spinner products, which are things that we're ultimately going to be computing in terms of, well, it replaces the bracket product of AJ with something where I subtract off G times AL, so nothing to the angle product. And conversely, for AL, it shifts the angle product, counting an amount proportional to A with the other spinner, and it does nothing to the bracket product. So we shifted these spinners J hat, I'll use hat more or less consistently to denote the shifted momentum, which is now a function of this parameter z, which is given by the original momentum, shifted by what you'll recognize as a null complex vector. And similarly, KL is shifted to KL hat, and that equals KL as a function of z, which is KL plus z over 2 times j minus the same null vector. So the first thing that we can observe is that these momenta are still on show. Because what do we get? Well, let's square out this object to get kj squared. Here's a cross term, so that's z times j kj l. And finally, there's this vector squared multiplied by z squared over 2. Well, this guy, of course, we already know its fate is the same as E plus, epsilon plus the positive velocity polarization vector, for that matter, the negative velocity one. Here we're going to get simply j, the angle product of j times j, times the angle product of L times L, so this thing is 0. Here the vanishing is only linear, but good enough. You get the angle product of j with j, so this thing is also 0. This thing, of course, was 0 to begin with, so it's 0. The shifted light is still on show. The other thing that we can note is that if we take the sum of kj hat and kl hat, then, of course, we're just going to add these two together, and this term will just cancel. It's the same vector. So we're just going to get kj plus kl. So momentum is still conserved, both within the two-particle system and more generally. Of course, if I were to take some partial sum of momenta, let's say kj and kj minus 1, if L is not j minus 1, then that will be shifted. And that's good. Because otherwise, if we change absolutely nothing at all, then needless to say, it's hard to see how we can get nothing. So we're going to, we shifted the spinners, we shifted the momenta, and our amplitudes are functions of the spinners. If you use the spinner helicity basis, then it's just a function of the spinners and the plus or minus. And so the amplitude, our amplitude, is also now a function of z. And I'm going to make the assumption that, and I'm going to show this holds for a wide variety of choices of theories and choices of shifts, but for now let's just make an assumption that as we take z to infinity, z is a complex parameter, so we let it go off to infinity in a complex plane, the amplitude vanishes. It doesn't really matter how fast, it vanishes some polynomial way. And we want to consider a contour integral. So let's consider the following contour integral. So we're going to remove the 2 pi I that would come from taking residues, and we're going to take the integral around the circle of a of z divided by z, and that circle c is the circle at infinity. So, well, let's see here. A of z is going to 0, and there's another power of z, so this thing is actually integrable. You can see that it's bounded by something that's going to be 1 over z squared, so this thing is 0. So we have a vanishing contour integral, and now we're going to go ahead and evaluate it by residues. So the first thing we have to figure out is why the hell am I asking you to consider this object? You know, I pulled this thing out of the hat, and I pulled the shift out of the hat. Well, the shift, of course, came from UCSW. People who invented that idea. But where did this integral come from? Well, there's one way. So what this equation says is that A of 0 plus the sum of at the other poles of A, of the residue at that pole, this is equal to 0. Well, that's already explaining to us at least why we want to think about this equation. Because A of 0, just one second, A of 0 is our original amplitude, of course. If we set z equal to 0, then we're back to the original momentum configuration, and that's exactly our original amplitude. So now we have an equation for our amplitude, admittedly in terms of a set of things which looks very obscure in its connection to anything that's not obvious, but patience, here, hold the question. Right now I'm working in Seagull. That's correct. And you can extend some of this technology to loop level, but at the moment there's no general theory of it, not because of the issue of branch cuts that you can take care of, but because of there's an incomplete understanding or an analog to one of the equations I'm going to write down a little bit later. So, no, that actually, this you can evade if it's not true, generally speaking. But if you're interested in that, then I can probably track down stuff in the literature, or you can track down using Inspire. It's not relevant to the core of the idea here. There are lots of poles in ASV. I haven't evaluated this thing yet. But all I said is that we have lots of poles at ASV, and we have to evaluate their residues. We haven't done that yet. So let's take things one step at a time. But what we have done is written an equation that says that we have a solution for A of 0. A of 0 is our amplitude. In terms of a bunch of other stuff, which is not clear what to do with right now, but just be patient. You have to be patient until tomorrow afternoon, but for the moment I'm just asking you to be patient for a few minutes. So it's not like one of these things in Ashcroft and Mermin where you find some equation for something you don't know, that they write it in terms of a whole bunch of other stuff which you don't know and don't know how to calculate. That's not where this is going. Okay, so in fact, we all asked, where are the poles in ASV? Very important question. Where are they? Well, let's think about this. So let's think, and even if we don't want to use it for calculating, sometimes for general argumentation, for abstract geometry calculations, it's still useful to think in terms of climate dynamics. And what we know is that there's poles in Z that might come from the spinor products that go into the polarization vectors. We'll actually see that's not the case later, but they might come from there. And the other source is, of course, we can have momentum in the denominators from propagators. So basically, the one class of poles that is non-trivial is going to come from propagators. So now let's just start, let's just write down some diagrams. So we have a diagram. There's some term of amplitudes, and there's some propagator, and then the rest of the diagram is on the other side of the propagator. So there's two basic cases we can consider. The first case is where there's some number of legs here, maybe they're all J, where J and L are sitting on the same side. And one thing we know for sure is this momentum involves Kj plus Kl, but that sum is independent of Z. So this propagator is free of Z. And whatever it is, however complicated it may be, there ain't no Z there, so there's no pole. The other situation we have is where J and L are on opposite sides of the propagator. So if we look at some diagram, this is some propagator we're so fixating on, L and J are opposite sides, then this depends on Z. So that's a good sign, because if it depends on Z, Z in principle can run all over the complex plane. So any polynomial equation has, right, we're setting that denominator equals 0, has a solution, therefore there is a pole. So that tells us something about what happens to this sum. Shall we erase this here? So that sum of all poles we can now replace with a sum over partitions. And it's partitions of the set of the external legs such that J and L are in partitions into two sets are in different subsets. It's a sum of all possible ways of doing that, and each possible way of doing that is going to give us a different pole over it. Moreover, we can actually write down the solution for that pole, because we now know we have some set of momenta on one side, some set on the other side. So just for the sake of the argument, let's label these A through B, and J is somewhere in the middle. There's a whole bunch of legs there. So what's going to show up in the denominator here, we actually know what momentum is going to show up there, independent of what is in the diagram. It's going to be Ka hat JB, or if we leave the hat there, I'll just hat here is sometimes redundant, but let me just put it there just to remind you, this thing is a function of Z, and its square is of course what's going to show up in the denominator. Well, we know what that shift is because this thing is a linear sum in J, and J is shifting linearly. So there's two terms. There's the unshifted term, which is equal to 0. That's just the sum of momenta A through B, the standard sum. It appears squared. And of course, the shift term is just a null vector, so its square is 0, so we only have a linear term. The 2 gets canceled by the 2 from the cross term, and we now have G minus Ka through B.